of the different mineral phases present uniformly across the entire model, both in the vadose zone and in underlying groundwater. And this is the same distribution of mineralogy as we discussed in the earlier one-dimensional example. The assumption in this particular model is that atmospheric oxygen can freely migrate through the vadose zone via diffusion, and this occurs where the water saturation is below 0.7. This is just an ad hoc assumption here as a demonstration. You can see the impact in the distribution of chalcopyrite after 14 years. And again, in this example, reaction kinetics are not being considered. Although it's largely oxidized and dissolved away in the vadose zone, there are zones of low permeability and high water saturation where it persists. Similar to the 1D results, you can see that there are areas in the vadose zone where malachite has precipitated. These are zones where the water saturation is less than 0.7 and atmospheric oxygen is present. After more time has elapsed, the results here are shown for 68 years. More of the chalcopyrite in the vadose zone has dissolved, and some of it is actually reprecipitating near the water table, contributing to the formation of an enrichment zone where reducing conditions are encountered. And finally, this is the distribution of cobalite, a secondary copper sulfide phase after 68 years, which is also part of a developing enrichment zone near the water table. And bornite, as shown here, which just occurs in scattered zones in this particular model. Let's have a quick look at the distribution of the weathering products. Here is the distribution of iron oxide created from the oxidation of primary pyrite in the vadose zone. And here is jarosite, which is a bit more widespread up in the vadose zone. So we're going to switch back to the other set of slides here for a moment. And I would be happy at this point to entertain any questions anybody might have. So let's take a short break here, if you give me a moment. Okay, so I brought up the chat feature. If you have any questions on what we've covered so far, we're going to be moving on to one more two-dimensional example in a moment that has a little different twist on it than the material that we just covered. But it doesn't look like anyone has any questions, so I will proceed. There will be another opportunity at the end of the slide set here in a bit to ask questions once again. So let's step through an additional example problem, this time again in 2 dimensions. If you'll recall from Module 5, there was a Freak C example that involved modeling surface complexation of trace elements into an aquifer mineral assemblage. Sulfuric acid, which was accidentally released as part of an industrial process, was spilled into the aquifer in this case, resulting in desorption of trace metals and an undesirable environmental impact. So here we will extend this problem into, basically convert it into a reactive transport model to provide some insights into the feasibility of cleanup. In this case, cleaning up the aquifer by manipulation of pH through the injection of chemical reagents. This is a modified version of a very similar simulation conducted for an actual site to help plan remediation. Aquifer heterogeneities and the interplay between flow and transport and geochemistry are once again a key part of this example. So a brief summary of the features of this particular model includes the following. The chemistry model was discussed previously in Module 5, so you can have a look back at that if you'd like after the webinar is done for a refresher. And the processes that we looked at included things that we're addressing here with the solution chemistry keyword block, equilibrium phases, and reactive surfaces. We're also including here a two-dimensional depiction of the aquifer, which is divided into a 1/2 by 1/2 kilometer block, discretized into a 50 by 50 grid. Groundwater flow in this aquifer is unconfined and is represented by specified head boundary conditions on the left and the right side. Let's have a look at portions of the transport input file first by keyword block. And again, this file is in the class materials in module 8 for you to review at your convenience. The free surface boundary condition is set equal to true in this example because this is an unconfined aquifer. Solute transport is set equal to true since we want to simulate reactive transport as opposed to only looking at groundwater flow. The grid is defined. Again, this is a 500 meter by 500 meter model domain with a 10 meter grid spacing. Under the media keyword block, the hydraulic conductivity distribution is read in from a tabular text file where values were assigned to grid cells by interpolation. In this instance, the hydraulic conductivity distribution was created externally using a correlated random field generator. The figure on the right shows this distribution of as log transformed hydraulic conductivity, with the blue shaded areas representing permeable aquifer materials such as sand and gravel, and the brown shaded material representing much less permeable silts and clayey sands. And finally, a specified head boundary condition is set on both the left and the right sides of the model, with the upgradient boundary associated with non-impacted background groundwater. And this composition was derived from average groundwater samples collected from upgradient wells at this particular site. Let's look at some of the results from FAST. Initially, the model was set up to run for a 10-year period without the addition of any pH influencing agent. This was really to set up plausible initial conditions. The groundwater flow field is shown on the left with the blue contour lines representing groundwater elevation contours and the arrows indicating the local groundwater velocity vectors. You can see an area of high groundwater flow to the upper left corresponding to the zone of high permeability. Toward the lower left, where permeability values are much lower, you can see that the groundwater flow velocity is subsequently reduced. The corresponding impact on solute concentrations, in this case dissolved iron, is shown on the right. You can see that after 10 years, relatively clean groundwater flowing in from the upper left has swept away some of the elevated iron concentrations or else precipitated the iron back into the solid phase via precipitation once the pH increases. Again, an effect of the influx of this unimpacted groundwater coming in through the model boundary. The high concentrations of iron remain to the lower left where there is much less flushing occurring. Very similar results are apparent for aluminum and sulfate. Aluminum's concentration is largely controlled by equilibrium with solid phase aluminum hydroxide, whereas sulfate is much more mobile. Because the background groundwater has not been impacted by sulfuric acid, concentrations of sulfate are lower toward the upper left. For 10 years, the concentration of some of the trace elements of environmental concern are shown here, with chromium on the left, arsenic in the middle, and nickel on the right. All three of these elements adsorb strongly to iron and aluminum oxyhydroxide mineral phases. There are low concentrations in the upper left portion of the model domain. This reflects readsorption of these trace elements back onto newly precipitated iron and aluminum oxyhydroxides that have formed in response to the increased pH in this particular area. Now let's take what we've created here, our initial conditions, as a basis for looking at a possible remediation approach. And the remediation that was considered, and again, this simulation is based on a real site, involved the injection